I'm Professor Rad, and this is Precalc video 220, the natural exponential function. So in this video, that's the function we're going to be talking about. So here's the definition for that function, and we can break it down and see why this is important. So the number e is going to be defined to be 1 plus 1 over n to the nth power as n goes to infinity. So what that means is we want to think about where this expression will go as n becomes super, super large. So for instance, if n is 1, we have 1 plus 1 over 1 to the first power. So that would give me 1 plus 1, which is 2 to the first, and I would get 2. If I have 1 plus 1 over 2 squared, that's going to give me 3 halves squared, which is 9 quarters, which is 2 1/4, so 2.25. Right? And then we're going to keep going until we get to an impossibly large number. So if I have 1 plus 1 over a super large number raised to that super large exponent power, what is that going to be? What are we going to be approaching? Kind of like an asymptote, right? So it turns out the value we approach is approximately 2.71828. So this is an irrational number similar to pi being an irrational number that's going to have lots of applications as we look at exponential functions. So that's why it gets this special name. The natural exponential function is the exponential function with e as its base. E is also sometimes called the Euler constant. And Euler is spelled E-U-L-E-R. It's a Swiss surname for mathematician Leonhard Euler, and he was like big guy in math. So just like Newton is a name that we all know from physics, Euler is a name that you should know for math. He did a lot of stuff, especially in graph theory and number theory and all sorts of things. So in fact, the notation that we use, a lot of it goes back to Euler. So for example, he's credited with popularizing the use of pi, of that symbol for pi. He's credited with our function notation to represent y, or even using I to represent the square root of -1. So a lot of the stuff that we know and love and use in math is because of this dude Euler. So I recommend you look him up. He's pretty impressive. So we can think of using e either for the natural exponent or e for Euler. Take your pick. So let's do an example of a word problem that's going to use this exponential function or use e in some capacity. Alrighty, so one of the reasons that e is called the natural exponential function, why we use e to the x, is because it occurs naturally when there's a lot of, well, just naturally in population growth and change. So we'll also see this with a few other examples later in this unit when we talk about radioactive decay and financial changes like growth of interest. But for this example here, I wanted to go with something really complicated actually. So we're going to use a logistic growth model. So you're not going to be expected for my class to memorize this formula or anything. I just wanted to bring in some alternate function that you might not have seen before. So if we have a function of this form, it's a logistic growth model, and A is the carrying capacity. What this means, what a logistic growth model means, is your environment has a certain set of conditions, right? There's an amount of land space, there are amount of like food resources, competitors or predators, things like that. So what a logistic growth model looks like is at first, the growth of the population will be exponential. So it'll have that curve we looked at when we saw our common functions, when we looked at e to the x or 2 to the x. But because of those constraints, because there are limits to the environment, at some point it's going to turn around and start to flatten out at its what's called carrying capacity. So the numerator here is the carrying capacity. It means you can't have a population larger than that. It's going to flatten out then because of limitations of resources and things like that. So here's our example. This example is about a lynx population, and it's modeled by this function L of t, L for lynx, and t is for time. So t is time in years, and specifically it's years after 1985. So when this study was first done, must have been started in 1985. So the initial time t equals 0 is going to be the year 1985. So when I look at this function, this number, the 15,000, that's the carrying capacity for the links. So that means the links can't exceed that population because there won't be enough land growth or land and resources and stuff. So that's when you'll start to see the population kind of flattening out. So for part A, let's see what the links population was when this started in 1985. So in 1985, that means that t is 0. So we're just going to find L of 0. So we substitute in 15,000 over 1 plus 3 e to the negative 0.08 times 0. Now, for my classes, when you're evaluating a function, this is the work I need to see. And if you want to skip right to the answer, feel free, go ahead to do that. So that's what I did. And I got 3,750. So depending on the calculator that you have, your exponential button, your E value may be found in a slightly different place. Typically, you will see it as like a second button for over another button. So for example, I've got a TI-30X2S here. And if I want to access e to the x, on this one, it's right above the ln key. So if I wanted to find that e to the x, I would hit second ln, and then that will open up a base of e. So your calculator may have it in a different spot, but look for it typically above the ln button on your calculator. We'll talk about ln in the future. All right, so that was the initial population of links living in this area at that time. For part B, they want us to estimate to the nearest 100 the links population for 2021. So to do that, first we have to figure out, well, how many years after 1985 is 2021? So we can just do some subtraction to do that. And there we are, 36. So 36 is how many years it's been since 85. So 36 is going to be the value we substitute in for t, since t is not the year it is, but how many years it's been since 1985. So we're going to find L of 36 and substitute into that formula again. So 15,000 over 1 plus 3 e to the negative 0.08, and this time times 36. Now this one I did not put in the oven and bake ahead early, so let's just calculate that together. So I've got 15,000 divided by 1 plus 3 times e to the negative 0.08 times 36. And that's giving me 12,838 and some change, a decimal piece. But they want this to the nearest 100. So we're going to round this to 12,800 links. And there we go. Now I will mention, if you're not getting this answer, when you throw this into a calculator, chances are you're missing some parentheses. So when you type this into your calculator, if your calculator doesn't have that fraction, like that top bottom mode, when you put divide for this fraction bar, you need to make sure you have parentheses around the entire denominator. Otherwise, it's just going to divide by 1 and then add 3 times e to this power. The other place you may need to insert parentheses is in this exponent. So you might also need parentheses up here, because otherwise what your calculator will do is it'll do e to the negative 0.08 and then multiply that result by 36. We need it to be doing this multiplication first and then use that result as the power. So some calculators will automatically put this parentheses here when you put in e. Other calculators do not. So you want to make sure you're checking your calculator and knowing how it works these functions properly. All right, but that's it for this video. In our next video, we're going to delve into some deeper properties of exponential functions. So I look forward to seeing you there. In the meantime, I hope you found this video helpful with Euler's constant or the natural exponential function, and have a marvelous day. See you next time.